Our second speaker. Actually, the screens. Our second speaker is Ben Moseley. He's coming to us from CMU. He's an associate professor at Tepper in the Operations Research Group. I have known his work on using predictions in order to improve the performance of online algorithms, and recently also run times. And today he's going to talk about machine learning for optimization. Take this away.
Well, thank you so much. I just want to thank the organizers for putting on this really amazing workshop and giving me the opportunity to be here. So I'm going to be talking about machine learning for optimization, and I'm in the Operations Research Group at Carnegie Mellon University. I also do a day a week at the really exciting startup, Relational AI. So the work I'm going to be talking about here kind of pulls from several different papers. So these papers are listed here at the bottom of the slide, so appearing in SOTA, ESA, ACDA, and NeurIPS. And these works were done with really an amazing group of collaborators. You know, the brains behind the work are really the students. My student, Thomas Lavastida, who just joined the University of Texas at Dallas, and student Chen-Yang Xu, who is visiting me at CMU for a couple of years. He's in Zhejiang University in China. And this is also done with Mike Denitz at Johns Hopkins, Sungjin Im at the University of California, Merced, Silvio Lotanzi at Google, Sergey Vasilevsky at Google, and also R. Ravi, who's in the OR group with me at CMU. So machine learning, as we all know, has been really transforming society. And so I can't think of an area of science and engineering that hasn't been touched on in some way from machine learning. Now, while that is true, you know, one thing that machine learning hasn't fundamentally changed, in my personal opinion, is it hasn't fundamentally changed the way we think about designing combinatorial optimization algorithms. But what we're asking in a recent line of work is, you know, well, could it? So one of the major questions we ask in practice often is, well, what is the right algorithm that I want to use for my given application? Right? And now what do I want? I want an algorithm that works really well for the exact kinds of inputs that I see in practice. Right? Unfortunately, though, this is usually hard to get. And the reason it's hard to get is because it's hard to mathematically characterize exactly what those input instances are. Right? So what do? Well, we usually revert to some more stylized form of analysis. We go to worst case analysis or stochastic analysis. But in both of these cases, we lose something. And if you go to the worst case, you're optimizing for pathological input instances that don't necessarily appear in practice. You go to stochastic analysis, it's not so clear in many cases that your data fits a nice distribution. And what we would like is something really tailored to the inputs we actually see. Now, while it's hard to mathematically characterize these instances, right, you know, usually in practice, we have lots of data available. And how do I think about this? I think of this as we've seen the problem in the past. We solved it yesterday, the day before that, etc. And so given that, well, maybe what we could do is mine this data for some information. Right? We take that mined information, we give it to the algorithm as a parameter, and then the algorithm self-tailors itself to the exact inputs that we see. And so this is the idea of this recently emerging line of work. And it's one that I'm just, you know, I'm super excited about this area. Okay. So for those of you who haven't seen this before, so Yossi talked about it, but let me do another warm-up example. So this example comes from a paper of Kraska et al., Sigma 2018. So here we have an array A of n integers, sorted. So we start with a sorted array. Good. Now over time, we get requests for queries. Right? And then you say, hey, is this number in the array? Right? And so for example, here, we get a request for 7, right? The array is sorted, so we just do a binary search, right, to solve this problem. We say, hey, yes, it's in the array, or no, it's not. Good. Right. So worst case running time, it's going to take log n time. You know, pretty much, you know, for almost everything we search for, it's going to be about log n time. Worst case, and also in practice. All right, but now consider the following idea. I train a predictor h of q. Okay, so a number comes in, and I'm going to predict where this number is in the array. So for example, 7 comes in, I say, hey, I think 7's here. Could be wrong, and so I'm going to start my search from there, looking for 7. I want to make it clear that this is something that's very natural that you might actually do in practice. So let me give you the following analogy before I describe this algorithm. Okay. So imagine you go into a library, a new library, for the first time. You're looking for a book by Tolkien. Okay. You go into this new library, you're not going to begin your search in the middle of the library, right? No, you've been to libraries before, right? So you're going to start your search near one end of the library because T comes near the end of the alphabet, right? And so you start your search there. Same exact kind of idea here. So we predict where the 7 is in the array, and we're going to begin our search there, right? So maybe our machine learning is wrong, so it's not exactly here. The array is sorted, so we look left, we look right, right? We know which direction 7 is in. We start going at powers of 2 in that direction until we overshoot the number, in which case we do a binary search inside. So let eta here be the error in our prediction. So from where we predicted the number to be to where it actually is in the array, or where it would be if we inserted it. Let's do a little back of the envelope analysis. So if eta is the error in our prediction, well, then what's the running time going to be? It's going to be log eta, right? So you do these powers of 2, right? It takes log eta time, binary search inside, log eta time. And you can be a little careful in practice, or you actually have to, train this prediction, but you can make it work. Okay, so we can compare the two, right? Worst case, binary search is going to take log n time. Our prediction algorithm is going to take log eta time. So what does this say? It says that with a perfect prediction, we get the best possible constant lookup time, the absolute best we can hope for. Right? In the worst case, eta is at most n, the length of the array. Right? Then we match the best worst case algorithm. And in between, we have a slow degradation in performance, right, depending on the error of our prediction. This is exactly the kind of thing we like in this model. Perfect predictions, right, go way beyond the worst case. If there's a huge error in the prediction, we're still bounded by the worst case, and in between, gracefully degrading in terms of the error of our prediction. So what's the punchline you should be taking away here from this example? The punchline is we can use machine learning, combine it with classic algorithm design to obtain better results. Now, the thing that's becoming, really exciting to me in this area is that what's emerging is kind of a generally applicable model for beyond worst case analysis, right? So beyond worst case analysis, super exciting area, lots of really beautiful results in this area. But the one downside of it is that often our models have to be tailored to, the exact problem. So we develop beyond worst case models on a problem by problem basis. But here what's emerging is a kind of widely applicable model we can apply to many kinds of problems. And that I think is really cool. So how do I think of this area? Right? So this area has been called learning augmented algorithms or algorithms with predictions. And the way I think of it is the following. So hidden from us is some distribution over typical input instances. I don't know what that distribution is. Good. Now we've seen instances in the past. So say I'm scheduling jobs, right? I've seen the jobs from yesterday, the day before that, etc. That's my training sample. It gets fed into some prediction algorithm, right? Predicts a parameter. And then my learning augmented algorithm takes that parameter as input, right? And now you see a new instance drawn from the distribution, and you tailor yourself to that instance. And so what do we think about in this area? Well, the major questions we think about are in this box. So first of all, what parameter should we predict? Not always obvious. Like, what is a good parameter to predict for your problem is often a main question that we ask. And then given that prediction, well, how do we algorithmically use it? I want to be clear here that everything inside this box is really just an algorithmic question. Right? There's no learning here. It's just what parameter should we be predicting, right? And how do we use that parameter? Now, it's also, I believe, equally important, of course, that our parameters, right, we actually can construct them from past data, right? And so we should be able to show some evidence that whatever it is we're using, right, we could actually learn it from seeing prior input instances, right? You shouldn't be using something that's, say, incomputable. So what's going on in this area? Well, I want to summarize the results. Yes.
Just a comment on the last point.
Yeah.
Isn't it important to have worst case guarantee when you don't understand how the predictions could happen? Like, current machine learning, we have very little theoretical result that they learn something that's learnable. Therefore, we need to have worst case guarantees. If you have something that is learnable, it might be less important to have worst case guarantees.
So you're saying that in some cases we don't really care if we can prove bounds on learning.
If you can prove that you can learn it, then you have good performance.
Maybe so if you can empirically prove.
Okay, yeah.
So, but I think in both cases, you're showing either theoretically or empirically that there's some evidence here that we could construct this well. I totally agree though. Thanks, Ola. Good. So what's the status of the area? So I want to summarize the recent work, but I can't do it. There's just too much work going on. There's a web page. I'll show it at the end of this talk, and there's over 100 papers on there in the last 3 years. So there's just a lot going on here. Now, through all these works, people have looked at many different models, and I think that's great. We've looked at different ways of thinking about this kind of problem. But what I would like to do is put forward, the way I think about designing algorithms in this area. So what I think is a nice analysis framework. So I'll call it the Earl framework. So it's 3 pillars: existence, robustness, and learnability. Good. So existence, you need to be able to show that there is some parameter for going beyond the worst case. Okay? So in that earlier example, the binary search, what do? Well, we said this location in the array. So that worked well for us. Predicting that location is the example. For a lot of problems, I want to be clear here, the parameter, thinking about what to predict is kind of the main question. Next is robustness, right? What do we want? We want algorithms that are, say, robust to minor changes in the problem input instance, or kind of are nearby in some way, right? You should be robust when things don't change so much. So, for example, go back to that binary search, right? If we predict the wrong location in the array, it's kind of okay. We can correct for this error dynamically. What would be a bad example, right? Imagine I just predict, yes, it's in the array, no, it's not. Not so great, right? I can't really check that without doing the worst case algorithm. And finally, learnability. So we need to show there's some evidence that our predictions are indeed learnable. So for example, maybe we could adapt the pack learning setting. We'll talk a little bit more about that a little later. All right, so what's the agenda? Our agenda is the following. So first, I'm just going to give it an example of an online algorithm. Right? And so we're going to parameterize the competitive ratio using the predictions. So this is in the same similar spirit of what Yossi was talking about. And then I'm going to talk about running time. And so here, the runtime is parameterized by the error in the prediction. So the problem I'll talk about is online restricted assignment, Makespan minimization. Good. So we're in the restricted assignment setting for this talk. So M machines, good. Jobs arrive in the online list model. What does that mean? Just think of them all arriving at time 0, 1 by 1. You assign it to a machine, you can't move it later. So job comes, you assign it to the machine, stuck there. Good. Then after you assign it, you see the next job in the list. That's the model. And now what do you want to do? Well, you want to minimize the makespan. What's the makespan? This is the maximum load assigned to any machine. Clear, make sure I said it clearly. M machines, N jobs, list model, one at a time, you assign, then you see the next job. You don't know the remaining part of the list. Every job has some feasible neighborhood. Okay, so it's restricted assignment. This means that each job can be scheduled on some subset of the machines. Okay, so N of J is a set of feasible machines for job J. Okay, so for example, maybe this green guy can only go to these 2 machines. This red guy maybe can go anywhere. There need not be any correlation between the jobs in this way. Now we could allow our jobs to have varying processing times. For this talk, what we're going to do is just assume the jobs are all unit sized. It captures the complexity of the problem, so it just makes it a little easier for me to talk about. And all the results hold for varying sizes. So just they're unit sized jobs. And what is my goal? My goal is to minimize the makespan. Good. All right, the maximum load, and we'll let T be the target. So this is the optimal solution. Right? All knowing optimal solution. If you schedule the jobs, knowing the entire instance. All right, so if I'm going to look at this problem, and try to design algorithms for it, well, what I might do is use the competitive analysis model. Right, so here we say an algorithm C competitive if the algorithm's performance relative to the optimal solution is bounded by C for any instance. What does that mean? It means that no matter what instance I see, the algorithm's makespan is at most C times larger than optimal. Good. All right, so I use competitive analysis. The problem's well understood. So what do we know? We know there's a log M lower bound and on the competitive ratio any online algorithm. Moreover, we know greedy is log M. And greedy just says, hey, job comes, assigned to the machine with the least load that it can go to. So from a worst case point of view, the problem's solved. Up to constant factors, these are matching. So makes it look like there's nothing left to do here. But the question is, is the worst case the right model? Do we really know nothing about the jobs that are going to come in the future when we're assigning the jobs? Now, a reasonable assumption here is that we have access to, say, last week's job sequences. If I'm scheduling a data center today, I've scheduled the data center yesterday, the day before that, etc. Right? And so given that, well, we have these instances, right? You know, what should we predict and how can we use this to schedule jobs in this setting? All right, so I'm going to show you some predictions that fail. I'm going to show you a prediction that works well in this setting and build some intuition. So first, let's think about things that don't work. Right? Now, when I sat down to solve this problem, this is the first thing we came up with, and it didn't work for us. One thing you might do is say, predict for this new instance, well, exactly how many jobs are going to be assigned to each machine in the optimal solution schedule. Right, so there's the all knowing offline. You predict, hey, how did that schedule assign the jobs? What's the load of each machine? Seems reasonable, right? Machines with a lot of load, just at an intuitive level, like these machines are very contentious. So maybe I'll try to reserve their space. Try that, but consider the following. Imagine I have some really difficult instance here described in blue. And now I create a new instance from this. Same job, same machines. But then I release a bunch of kind of dummy jobs that can go anywhere. Right? Now what does the optimal do? It just smears all these dummy jobs in all the holes. I don't know which job's which, right? So what happens now is maybe all the machines in optimal have the exact same makespan. So I gave you that information. It's worthless. Every machine has the exact same load. Right? So just an intuitive level, I'm trying to show is like this isn't such a useful prediction. Seems natural, but not so useful. Another thing we thought about was dual variables. So maybe we would predict the dual variables for the natural linear program for this problem. This is a pretty good idea. And so in fact, this works for a related problem of matching in the random order model. And so this goes back to some work long before this prediction model stuff by Devinar and Hayes and D et al. So think of bipartite matching. One side of the graph is arriving online. The guy comes, you want to match him. Good. All right, so they looked at this in the random order model. And what they do is they read in a small fraction of the nodes in the random order, don't match them. Use them to construct dual variables. Then using those dual variables in complementary slackness, the dual variables that you construct tell you how to assign the remaining jobs. Like it gives you an assignment rule. Right? So effectively what they're doing, they're reading a small portion of the input in the random order model, they're learning dual variables on that sampled fraction, and then they use that to get an online algorithm to do the matching. Good. And in fact, they can show doing this for the random order model, they get a near optimal matching. So, I mean, given the matching is very related to our problem, you might think you do the same thing. It might work, but we think the dual variables in this case were too fragile. And basically, what happens is the following. So you can write down the primal and dual. If I gave you the optimal dual variables, it gives you an online assignment rule that if they were, they're truly optimal, you'll get a good assignment online. But if there's error in them, we have problems. So really small changes, like just a 1 plus 1 over poly n factor change in these dual variables completely changes the assignment in some cases. So we couldn't work with them in terms of robustness.
Ben?
Yes, please.
Does it change the assignment or the assignment quality drastically?
That's it. Yeah, good. So we couldn't prove it. So I don't have a lower bound, but it's a very interesting question. And then we worked for a while on it, and it's just like this, but it's changed so much that we couldn't prove it. Thanks for
it's surprising because this is definitely on their papers. They learn the duals based on random order, right?
Yes.
But they should be like noise.
Yeah, but yeah. But matching is somehow the objective is less sensitive. That's the issue.
Question.
Oh, I see, because it's a sum of it. Sorry.
Yeah, please.
You are talking about fractional assignment here or integral assignment? Because does the integrality gap?
Go ahead. It was fractional. Yeah, thank you. So what came out of these ideas, like this is a warm up. Kind of what came out of here that, okay, so these don't work, but through lots of different ideas, those here and others we thought of is like, what we want to know is something about how contentious a machine is. That seems like an important quantity for the restricted assignment problem. So we're going to predict something like this. So our idea is the following. And we're going to predict a weight for each machine, single number, and an intuitive level. Lower weight means the machine is more restrictive. Higher weight means less restrictive. I'll tell you what the weights are in a second, but there's the framework. Framework is predict weights. Weights are going to give me an online assignment rule, but it's going to do it in the fractional world. So we're going to smear jobs fractionally using these weights. And then separately from this fractional assignment, we'll round it to an integer solution. Okay, so what are the weights? Well, so for each machine I, we're going to have a weight, WI. Good. And now for a set of weights, I'm going to tell you how to fractionally assign the jobs. How does it work? Well, each job J is assigned to machine I fractionally as follows. Like the job comes, it looks at the machines in its neighborhood, and it smears itself proportionally. So each machine I, it'll be the weight of that machine over the sum of the weights in the neighborhood. It's just a proportional assignment according to weights. Now, the thing to notice here, right? If I gave you the weights, this gives me an online algorithm, right? For the fractional problem, right? If I had these weights, then I just assign them this way. Now, of course, you might be looking like, what, you know, with this assignment rule, why should there exist weights like this that are close to optimal? That's not so clear. But, you know, for the weights, there is an online assignment rule, right? If we do it this way. Okay. So the first thing is just showing existence, right? So the existence part of the framework, right? We want to show that we could predict these weights. So if we let T be the optimal make span, good. And we show there exist machine weights that give us a fractional load of 1 plus epsilon T. You can give me an instance, I can compute weights. So it's a totally offline problem. We give a polynomial time algorithm to compute weights, or if I assign them in the way it's on the previous slide, right, I'm near optimal. Okay, good. All right. Now there's another problem, right? What do we want? Well, we want integer assignments. So imagine I give you perfect weights. It gives me an online algorithm to do the fractional allocation, right? But I want to round it to an integer solution, right? But luckily we can do that. So in our work, we show a result, but this has since been improved by a paper of Lee and Sheehan in ICML. What they show is, say you have like T prime is your fractional load. So that's what you're trying to shoot for. Jobs are coming, they tell you the fractional assignment, you just need to round them online, right? Right. So it's nothing to do with learning now. It's just a rounding problem. Good. And so they show that you can do this with losing log m. Right. Now you might be wondering, like, why are you losing this log m? Well, in fact, we show in our work that this, no, I should be clear, this is a randomized algorithm that succeeds with high probability. We show that for any randomized algorithm, there's a lower bound of log m. So there exist fractional assignments where you're going to have to lose this log m factor. You might be wondering, like, what about deterministic algorithms? Interestingly, for deterministic algorithms, we show that there's a lower bound of log m on the rounding. So even if I give you the fractional assignment online, deterministically, the lower bound matches the worst cases if I gave you no information. I also should be clear, this is all about the really difficult case when the make span is really small and optimal. Like if the make span in the optimal solution is large, like bigger than log m, you just do randomized rounding. You can get a near optimal solution, no problem. Good. So this shows that these weights exist, right? So this is the existence part. Yeah, totally.
So the log lower bound is also with respect to fractional solution constructed with weights, or you have a fraction solution. But for constructed with such weights or any fraction, like.
Oh, good. So yeah, we just look at this totally separate problem where I just give you the.
It could be that I could round those better.
I guess so. Yes, that's true. That's true. Thanks. You might use some structural property.
But sorry, I might misunderstand the model, but isn't it like if you just have one job that takes the same size on each machine, is it the fractional solution going to be like a factor that?
Okay, good. So I'm hiding the fact that my unit time jobs here, that I'm assuming the optimal solution is at least one. Generally speaking, if a job has some processing time, just let's assume opt has at least that processing time. And this all is true. All right, so what do we have? We have the existence, right? Next part is robustness. Right, what if the predictions are wrong? Right, so we have an online algorithm. I predict the weights, and I'm going to use them to assign the jobs. Good. All right, so the robustness guarantee we give is the following. So for each of the weights, we look at the maximum relative error. So the weights I predict relative to the weights I should have been given. Look at the max relative error, eta, good. And we show that we can kind of correct for this error, and we give a competitive ratio that's the minimum of log eta and log m for the fractional problem. So if you just use the weights, you lose something polynomial in eta. So our algorithm realizes online that there's some error and corrects for it dynamically, pushing it down to log eta. Good. Now you can combine this with that rounding, and overall, what do you get? Well, you get the minimum. Oh, and I should say here, right, there's the log m. So we get the min of log eta. If the error is really big, right, we're still bounded by the best worst case algorithm. We throw in the rounding, and then we get the minimum of log m, so the rounding times log eta. Right. So in particular, if the predictions are really good, we're going to do great, right? And then in the worst case, we're still bounded by the log m. Please.
Do you have to do work to show that the log m disappears from the second branch in the corollary?
It's not so difficult.
Okay.
Yeah. It's not. All right, so then what do we need? Well, we also want to give some evidence that these weights are indeed learnable, right? That you could construct them from prior instances. All right, so let me talk about ways you could do this for a general framework you'd apply to any problem. All right, so imagine there's some unknown distribution D, like there's a distribution over input instances, good, right? Something you might want to do is say, hey, I want to compute, say, the best prediction for my algorithm. What does that mean? I want to get the prediction that an expectation or my algorithm has the best performance. Good. All right. And now a question you could ask is like, well, okay, to show that this is computable, give a polynomial time algorithm that using a small number of samples, we can compute a prediction where the expected performance of the algorithm with the prediction is nearly as good as having the best prediction of my algorithm. Notice here, they're not comparing to the optimal solution. Right? So all I'm doing is saying I'm finding the best prediction for my algorithm, right, for this particular distribution. Okay, so you can look at that model. So this model is similar to pack learning, or this really exciting area people have been working on, data-driven algorithm design. So that's one way you could look at it. Another way you could look at it is by going competitive analysis. So before we were comparing the algorithm to itself, best prediction for the algorithm. And another thing you might do is show that with a small number of samples, you can construct a prediction, right, where the expected performance of the algorithm is nearly as good as the optimal solution. And of course, this is going to be much harder. So here I'm comparing to opt, not the algorithm itself. So what do we show? But this is just to give some evidence that these weights are learnable. Right, so we show that D is a product distribution and the optimal Makespan is large. So two very strong assumptions. Removing these assumptions is very interesting to me. But then we show that indeed you can compute weights given a polynomial number of samples, polynomial time. You can compute weights that are nearly optimal as compared to the optimal solution for that distribution.
Doing like empirical risk minimization on the past sequences.
Yep, exactly.
Okay. Do you know of like sort of settings here where you don't want to do empirical risk minimization?
Well, yeah, for some settings you could just prove they're good, like compared to optimal or something. Using a combinatorial or it's totally reasonable. Like just do stochastic analysis, right? And so you throw away the URM and just bound it. Totally possible for the particular distribution.
Okay. But I'm imagining maybe in some matching settings.
Yeah.
Do empirical risk minimization.
Yeah.
You might overfit to the points.
Sure.
You might want to take like more sort of like the AdWords type weights. So I'm just curious whether there's like in your experience, is learnability usually just try to prove them using ERM, or do you know of cases where to prove learnability you need to sort of hedge your weights?
Totally. I'll have to think a little bit offline. Yeah, I can't. Nothing's like coming to my head.
Okay.
Yeah.
I guess on that point, there's like this, and there's also robustness fixed at during the algorithm stage. So like, how much do you need to be robust here versus in the algorithm?
But right, of course. Yeah. So there's a question about being robust here in the learning part versus the online algorithm part, where they're kind of measuring different things. Right? And so they're just different bounds. Yeah, that's an interesting question. I mean, generally that you show different things there. Yeah. Beautiful. Coming from the new model. All right, so that does it all. So existence, robustness, and learnability. Earl model. Right, so we showed the weights exist. Go beyond the worst case. You gave me good weights. We're robust to errors in the predictions, right? And then we give some evidence that they're learnable. All right, so that's what I want to say about online algorithms. Just to mention here, like there's just a ton of work on online algorithms.
Sorry.
Yes.
What if I say that there exists some good weights? I don't assume my distribution to be a product distribution. Would that be a possibility, or you have a counterexample that some?
Oh no, counterexample.
Okay.
Yeah. So that's something I thought about. I just don't know the answer. So.
Okay.
Cool. So so there's just tons of work out there. It's super natural, like that people be considering this, right? So you're using predictions to deal with uncertainty in the online setting. Very natural case of using machine learning, right? And so that's where most of the work has been done. Why don't I go back to the original question, right? So go back to the beginning of the talk. We were looking at this binary search, right? That's where we're improving runtime, right? Got to think about, can we speed up algorithms using these predictions? So this brings us to the idea of warm start. So many problems are solved on similar input instances over and over again in practice. So really anything we're going to spend a lot of effort trying to solve, we usually solve more than once, right? Scheduling yesterday, scheduling today. Yet when we analyze the running time of our algorithms, it's always in the worst case. Right? We just throw away that information that we have from solving them in the past. Right? So we're like Dory here, like we get a new scheduling instance, we totally forget about the jobs we scheduled yesterday. Why are we doing that? Right? What are we going to use some of that information to help us solve our problems in the future? Right? And so that brings us the idea of warm start. Right? So maybe we can warm start the algorithm with something from the past. Now, I did some literature search here. I could find combinatorial algorithms that use warm start, but they were all heuristics, so they didn't have theoretical guarantees. So one way of kind of viewing this work is putting the warm start on a theoretical foundation. That said, if you know of works, I would love to read them. So good. So what are the pitfalls, right? So as before, we want robustness and learnability, right? So if I predict something, I predict for the running time, you know, it might not be feasible, right? So if I predict something, I might start in an infeasible state, right? So somehow I need to get back to feasibility is going to be a big issue. Then even if what I predict is feasible, somehow I need to very quickly optimize. So I need to do better than what I could do without the prediction. And then as before, right, of course, I want to show these things are learnable, whatever my starting states. So what's the problem I'm going to look at? I'm going to look at weighted bipartite matching. Good. So we got a bipartite graph. We have costs on the edges, Cij. Think of it as a complete graph for this talk. Let's say we want to compute a min cost perfect matching on this complete graph. Now, you might be wondering, like, why don't I look at max weight matching? Because in practice, often to solve that problem, you would use the Hungarian algorithm. First thing it does is it converts it into a min cost perfect matching problem. So that's what we're going to talk about. All right. So what are we going to predict? Well, we could predict edges in the optimal solution. Some intuitive level that's felt too brittle to us. And the reason, and it might be okay, but we don't have the lower bound. But you know, if I change the weight of one edge a little bit, like the optimal solution might take an augmenting path, switching all the edges in the solution, right? So it just seemed brittle to predict edges. So what we're going to do is we're going to use linear program duality. So what do we got? We got the primal and dual, right? We're trying to minimize the cost of the edges we pick. So x's, do I pick an edge? 0 not. Good. For every vertex, right? We got to pick an edge adjacent to it for perfect matching. Good. We're going to minimize the cost, so min cost perfect matching. Right? So what's the dual? For each vertex, we have a price. So yi is the price on vertex I. Good. And what do the constraints say? It says, hey, for every edge, the sum of the prices on the endpoint is going to be most the cost of that edge. Good. And what do we know? Well, we know by complementary slackness that edges in the optimal matching, they're going to have a tight dual constraint. All right, so let's say we want to solve this problem using the Hungarian algorithm. How does it work at a high level? And I can give all the details, but So it starts with the dual values at 0. So the primal dual algorithm starts with the dual values at 0, and it's going to raise them up over time. At every point in time, it maintains a feasible solution. Good. All right. Now it goes through these iterations, and so in each iteration, it's going to push up some of these the prices on the vertices. Then what it does is it finds all the tight dual constraints. And these correspond to edges, throws them into a set. Then you go find a max cardinality matching on that set. And if it's perfect, that's a proof that it's optimal. So it's a perfect matching. If it's not, what do? Well, by Hall's theorem, right, there's some set like that violates, right? There's some set that violates Hall's theorem, and this immediately is going to tell you, which dual variables to push up in the next iteration. High level, this is how it works. Good. So notice here, it starts with the dual values at 0. What are we going to do? Well, just predict the dual values. Very natural. Start the algorithm from there. All right, so we're going to warm start Hungarian with these predicted dual variables. First thing we're going to run into is a feasibility issue, right? We want to be robust, right? And so if I predict these prices, right, they might violate the dual constraints. Right? Somehow I need to deal with that, right? So the Hungarian algorithm always maintains something that's feasible. And so in particular, right, it might be the sum of the prices on an edge is more than the cost. So what's our idea? Our idea is we're going to take these prices and reduce them as little as possible to make these constraints feasible and do it fast. We set up the following optimization problem. It's really simple. It just says, hey, this is how much your delta I is how much am I going to reduce the price vertex I, and you got to reduce it enough to make the constraint feasible from the original. Right. So we don't solve this directly. We give a simple greedy algorithm, and it gets a 2 approximation to this in linear time, and this is good enough for us. Good. Right. So predict the duals. We basically project back to feasibility using this greedy algorithm. Right. So they could be infeasible. Move it to feasible. It's, you're reducing the values basically as small as possible, nearly as small as possible. Good. And then from there, Hungarian algorithm doesn't care where you are. It just starts. You can just start running it. So our theorem says the following. It says, hey, the runtime is going to be the L1 norm difference of the predicted duals versus the optimal duals times the time it takes to run the cardinality matching. And you can show that you're bounded in the worst case by the worst case runtime of the Hungarian algorithm. So intuitively, if this is really close to optimal, like it's reducing the weighted matching down to cardinality matching. All right, so I have not much time left, but let me just go over some experiments. So you might be wondering, well, does any of this stuff work, right? Well, okay. So first, let's look at some synthetic data. And so what is the synthetic data? We just here we want to show like the conclusion we want is if there's something to learn, right? Our algorithm does well. So good. So we plant a matching of very low cost edges in a bipartite graph. Then we add noise to all the edges. Some of the edges get kicked out of the matching by doing this, that with the planted matching. But in general, that most of those edges remain in the min cost matching. And so there's something to learn. So good. And what do we see? The learn dual algorithm is performing fewer iterations of this cardinality matching. Fewer iterations of the Hungarian. Good. So that says, hey, if there's something to learn, we learn it. Now, what should you also expect? Well, if there's nothing to learn, the algorithm should not perform better. But we hope it doesn't perform so much worse than Hungarian, right? So what do? Well, we really crank up the noise here. We add all the edges. Basically, as you really increase this noise, what's going to happen is it's going to kick out all the edges that we planted there, right? And then it's just a random graph. And of course, with a random graph, there's nothing to learn. And so we see we're doing better. And then we revert back to the performance, close to the performance of the Hungarian. Not too much close, too much close. So that matches our intuition. This is good. So then we are like, okay, what about real data? Good. So we ran in a bunch of geometric data sets. So here we're finding, the min cost matching of these points where the edge lengths are the Euclidean distance. And we just subsample these. I can get more into how the sampling goes. But basically, what do we see? We see we're never running worse than Hungarian. Sometimes it's pretty modest, our improvement. In other cases, we're getting a 10 times speed up. Okay, so what's the conclusion? Maybe there's something going on here where we can get some speed ups by predicting. And finally, our theory says we need a polynomial number of samples, right, to be able to construct good dual variables. Well, what about practice, right? So how many samples do we need? We ran in all the real data sets, and basically what we observe is that after a small number of samples, we see separation between the learn dual algorithm and Hungarian. So we don't need so many samples in practice. We don't need like proportional number of nodes in the graph or something to start getting some proof. Good. So that's what I wanted to say. So interesting questions in this model. So you could look at your favorite problem, of course, but some things that I'm interested in is like, can we separate predictions, right? Are there predictions that aren't learnable, but way more powerful than learnable predictions? Intuitively, that makes sense, but I have no proof of this. I have no example. So that I think that it's an interesting question. Generally, you could look at this model for online algorithm designs to help you cope with uncertainty. You might use it for running time offline. You might design learn data structures. But there could be other applications for different models. For instance, I think it's ripe for, say, figuring out how to apply this technique or something like it to, say, some stochastic optimization problem. Good. And so I'll leave you here with this link. So this link, this is where people have been dumping papers. Anything that appears, you can add it here. So there's this huge list of papers, and people have been tagging it with what's going on in the paper. With that, thanks so much for your time, everyone.
Let's take a couple of questions and then.
So in this framework, you're using like a frequentist approach. Yeah, I'm thinking about like point estimates and how can I get that. But have you does this? Are there settings where taking like a more Bayesian approach?
So that is interesting, and it's something that I've been trying to think about. So I can't point to a specific way to look at that, but it seems like a very nice question. How to do this in a more Bayesian setting where making decisions over time and so on, collecting some condition information.
I guess now the best way is the way that you define learnability is through kind of assuming a distribution of resources, and in some sense, like the whole point of having predictions was we do not have stochasticity, and now we're forcing that inside the.
Yes, if you demand that you're good for the stochastic distribution, then it's almost like you're just looking at a stochastic model. Exactly. But you could still, it's different to say I have the best prediction for my algorithm. And you don't have to just have.
You're shown that empirically very you can perform much faster with very few samples. Do you think that this is due to the fact that you are learning faster than the theory predicts, or because you are less sensitive to error than theory predicts? Because there are two types of error: learning and robustness, sensitivity.
You just say the question.
So you have the norm one error that bounds like how error in prediction can impact performance of algorithm, and you also have like an error on how fast you can learn.
Yeah.
So my question is, which one do you think is inflated in theory versus practice?
Definitely, I think the volume of samples is huge, and probably you can push that down.
So the learnability.
Yeah.
Do you think the learning rules can be applied to solving general linear programs?
I think it's a very interesting question. I don't know how to do it, but it's a super interesting question.
Let's take more questions line. Back at 11.